I guess thank you for coming. Yeah. So I don't look like a fool talking to myself. Okay, so today is our last lecture. We're going to have a short lecture because we only have one topic to cover. Basically, we want to learn how to calculate the shell thickness of a pressure vessel. Yeah, out of the so many equipment in the list, in the cost table, right, I chose pressure vessel where I'm going to cover in the lecture because this is where your most of the economic calculation will be needed for, yeah, to calculate the cost of your reactor, your distillation column, your flash drum, maybe absorption and so on, okay? So today we're going to be a mechanical engineer. Yeah, we're going to follow the code in the ASME boiler and pressure vessel codes, yeah, to calculate the shell thickness. So ASME is American Society of Mechanical Engineers. Okay. Okay. Um, so today we're going to learn. First, I'm going to tell you the difference between pressure vessel and tower. Yeah, so when you see vessels, it means it's a cylindrical vessel where there is no internal inside the vessel. Yeah, so basically you use it for reflux drum, flash drum, or if you use it for reactor, there will be a catalytic bed inside the vessel. Okay, so that's what we call pressure vessels. For the towers, it's a vertical vessel where there will be internals. Yeah, the internals will be the sieve trays, the structure packing, and so on. Okay, so the cost of a vessel depends on the weight of the vessel. Yeah, and the weight of the vessels depends on the height, the inside the diameter of the vessel, plus the shell thickness. Okay, so that's what we're going to learn, yeah, how to calculate or how to choose the proper shell thickness. Okay, before we do that, let me just show you what are the parts of vessel that there is there. Yeah, so for example, when you design your continuous flow reactor next semester, in addition to choosing the diameter and the length, you also need to choose the nozzle size. Yeah, because the nozzle size will influence the velocity of your reactant going into the reactor. And when you have a packed bed, right, the velocity will influence the pressure drop. Right, the pressure drop for a gas phase reaction will influence the concentration, so it will influence the reaction rate as well. Yeah, that's why the nozzle selection is important. Yeah, it's not something that you can ignore. And next semester you will get the chance to investigate yourself, right, using rules of thumb or from literature, what kind of nozzle design is needed for a packed bed reactor. Okay, so another thing that you have to include is the skirt and the saddles for supports, platform and ladders and so on. Yeah, the costing for these parts is also included in the correlation that we're going to use. Okay. Okay, so this is one illustration of a packed bed reactor. Right, so today we're going to learn how to size the shell thickness. Yeah, the shell thickness will depend on the operating pressure and operating temperature of your reactant. Okay, so that's what you're going to learn. For the other parts, you need to use rule of thumb. Yeah, for example, when you have a packed bed reactor, you must have a catalyst support here, right? And the height of the catalyst support will depend on the height of the catalyst bed. Yeah, and those numbers can be found from the rules of thumb. Yeah, I'm not going to cover it here, but you can easily find references in the library, yeah, for next semester. Okay, so that's the support. Another important thing will be the insulation. Let's say you want to run it adiabatically. You must also know how to size the thickness of your insulator, yeah, and how to choose the materials. Yeah, so that's from your heat transfer module. Okay. And then the next one will be the distributor. Yeah, if you remember when you took the unit ops 2, right, with Prof. Raymond, you deal a lot with fluidized bed, and I'm sure you learned something about liquid distribution, and it's something that must be in the design as well. Okay. So the rest are not as important as the one that I highlighted in red. Okay. Okay. So. Next semester, you will also be asked to sketch your design. Yeah, so for example, for reactor, you will be asked to come up with a sketch like this. So you have to draw it to scale, and you have to indicate the length of your catalyst bed, or the height of your catalyst bed, and the height of your catalyst port, what kind of distributor that you are using, and you have to justify your selection. Okay, so that's just a preview what you have to do. Okay. Okay, so now let's start with the shell thickness calculation. Okay, so like I said, the cost of a pressure vessel depends on the weight. Yeah, to get the weight, we must be able to calculate the shell thickness. Okay, so basically, if this is the cross-sectional area, oh, I cannot see. Yeah, so if this is the shell thickness, if this is di, the internal diameter, and this is the shell thickness, the weight can be calculated from the following. Yeah, the final equation is given in your lecture note. I'm just going to show you how they got this equation. So basically, the area of the whole thing, di plus 2 ts squared, right, times the height or the length, right? So this will give you the volume, right, of the cylinder, right, of the whole cylinder. But since this is a hollow cylinder, right, with a certain thickness, you have to minus the one inside, right, times L as well. So this will be the volume. To get the weight, you have to multiply by the density, right, of your materials. Okay. Okay, so this becomes di square plus 4ts square plus 4 di ts minus di square. Yeah, so the di square will cancel out, and you are left with these two terms, right? So if you do some manipulation, this is what you will get. Okay, this is the final equation. Okay, so the point 8 here is to take into account the two elliptical head for your cylinder. Okay. Okay, so from this equation, we know the inner diameter because this is something that you choose depending on the flow rate of your fluid. Yeah, so for example, for the distillation column, the selection of the inner diameter will depend on the vapor flow rate. Yeah, basically you want to prevent flooding or liquid whipping in the trace. Yeah, so we know how to select the I. Okay. The length is also known, usually from the number of stages, right? Or for reactor, it will be from the conversion that you want to achieve. Okay, so what we don't know is TS, yeah, the shell thickness. Okay, so that's basically what we are going to calculate. Okay. So the shell thickness, right, can be calculated from the following equation. Yeah, so basically, Ts is equal to Tp, the one from the equation here, plus T to take into account corrosion. Yeah? So this number is usually 1/8 of an inch. Okay. Okay. So now we know we need to know how to calculate Tp. So the equation is given here. It's also in your textbook. So in this equation, there are several unknowns. Di we know. PD is the design pressure. Yeah, so it's not the operating pressure. It's design pressure, which we're going to learn next what it is. S is the maximum allowable stress at the design temperature. We'll also learn how to do it. E is a constant. It's basically the welding efficiency of your column. Okay, so we need to know how to calculate design pressure, S, the maximum allowable stress, and E. E is just a constant, yeah, so it's not needed, we don't have to calculate. Okay, so this is for the horizontal vessel, yeah? Horizontal vessel. For the vertical one, you need to add the wind load, right? The thickness to take into account the wind load, okay? So it becomes Ts is equal to Tp plus Tw for the wind, right? And then T corrosion. Yeah, so this number is also 1/8 of an inch, okay? Okay, so now let's start with the horizontal vessel. Okay, so there are, basically this is just a recipe that you just need to follow step by step, right? It's very simple to do. Okay, so we want to calculate the design pressure. The design pressure is a function of the operating pressure, PO, okay? So you know your operating pressure, and depending on the operating pressure, your design pressure will be different. Okay, so there's a typo in your lecture notes. This one, it should be 5 instead of 10. Okay? And another thing that you have to note here, everything is calculated in terms of the gauge pressure. Yeah, so it's not the absolute pressure. Gauge pressure meaning you have to subtract the ambient pressure from your operating pressure. Yeah, so the ambient pressure is usually 14.9 psi, right? So you have to subtract 14.9 psi to get psig, yeah, the gauge pressure. Okay, so depending on the different operating pressure, you get different design pressure. However, there is another limit, right? So let's say you have a very low operating pressure. If you have a very low operating pressure, you will get PD around 10 psig. Yeah, so let's say you substitute that value into the equation that we have earlier. If Tp is lower than or smaller than the minimum thickness, you have to set the thickness to these numbers, yeah, depending on the Di. Okay, so let me repeat. So let's say your operating pressure is too low, so your PD is also low. You calculate Tp from this equation. The next step is to check whether Tp is larger than the minimum pressure over here. Yeah, if Tp is smaller than the minimum pressure over here, then you have to set the Tp to this minimum value. Okay, so you calculate Tp, then you check with the Tp minimum. Okay, so that's how to calculate design pressure. The next step will be to calculate the maximum allowable stress. Okay, so the maximum allowable stress depends on the design temperature now, not the operating pressure. Yeah, depends on the design temperature. So the design temperature is defined as the operating temperature plus 50 degrees Fahrenheit. Okay, so that's TD. Okay, so for different TD, and for different environment in the vessel, you can use different values of S. Okay, so for example, if TD is between this temperature, and you know that it's non-corrosive, and you also you do not have any hydrogen inside the vessel, then this is the rule of thumb. Yeah, you use S equal to 13,750 psi, and you will use carbon steel. Okay, for other condition, especially when you have hydrogen present inside the vessel, you have to use the one in this table. Okay? And so that's for S. The next one will be E. Yeah, so like I said, E is a constant. It's either 0.85 or 1. Yeah, it depends on the value of your shell thickness, TP. Yeah, however, as you may have noticed, right, when you need to know the value of E, you don't know the value of TP, right? Because TP is the thing that we want to calculate. So the approach here, we guess the value of E. Yeah, so we guess whether it's either 0.85 or 1. Yeah, and then once you get the TP, you check whether your guess value is correct. Okay, so that's the approach. Okay, so that's for horizontal vessel, right? We just need TP, then you add the corrosion thickness. Okay, so now for the vertical one. Okay, vertical vessels. For the vertical vessels, it will be like this. So this, when you have vertical vessel, you have to take into account that there will be wind. Yeah. So for example, this equation is valid when there is a wind in the velocity of 140 miles per hour. That is uniformly distributed. Yeah. So it won't survive a typhoon. Okay. So this is the standard. Okay. So when you have a vertical vessel, the thickness in the top will be equal to TP. Yeah, similar to what we did for the horizontal vessel. Okay. So the one in the bottom will be TP plus the wind. Yeah. Okay. And then the average shell thickness will be T top plus T bottom divided by 2. Yeah. So, and then your final one will be TS equal to TV plus T corrosion. Okay, so that's the difference between horizontal and vertical vessel. Yeah, basically, you add the wind load, and then you take the average top and bottom before you add the corrosion thickness. Okay. So in these equations, right, the only unknown will be the T wind, right, the TW. Okay, so the equation for TW is shown here. DO is the external diameter. So what is DO? It will be the inner diameter plus 2 times the shell thickness. However, in this equation, the shell thickness here is always assumed to be equal to 1.25 inch. Yeah, so DO is always equal to DI plus 2.5 inch, yeah, for this equation. Okay. The rest we know, right? The L, the height, and the maximum allowable stress is known. Okay. Okay, so that's it, right, for the recipe. So now let's do an example, yeah, to make sure we know how to use these equations. Okay. Okay, so the first one will be a horizontal vessel. right? So the inner diameter is 78 inch. The height or the length for horizontal, right, is 480 inches. The operating pressure will be between 482 to 484 psia. Yeah, it's not the gauge pressure, so you have to subtract the ambient pressure to get the correct design pressure. And the operating temperature is between 800 and 850. Okay, so now we want to calculate the shell thickness. Okay. So for the design pressure, we choose the highest operating pressure. It will be 484 psia. So to get the gauge value, you minus 14. So this is the gauge value. And then if you go back to the table, 484 psia, is between this range, right? PSIG, I'm sorry, PSIG. So you have to use the following equation, yeah, to get PD. Okay, so that's what we did. Okay, so if you use this equation, you will get design pressure equal to 546 PSIG. Okay? And then the next one will be the maximum allowable stress. Again, we choose the highest operating temperature, 850. You plus 50 to get the design temperature equal to 900. And then you can use the table, yeah, in the slide. And from that table, you know that S is equal to this number. Okay, so now the next step will be to guess the value of E. Yeah. Okay, so for this example, we're going to guess that the shell thickness is larger than 1.25 inch. So we're going to use E equal to 1.0. Yeah. Okay, so now we have everything that we need to use equation 1. So you can calculate the shell thickness without the corrosion using this equation. So it's equal to 1.667 inch. Okay? So 1.667 inch is larger than 1.25. Right? So your guess is correct. So you don't need to do any correction for the value of E. Okay, so this is TP. So now we add 1/8 of inch, right, to get the final shell thickness. Okay? So the next step is to know the commercial size for your carbon steel plate. Yeah, because the carbon steel is not sold in different sizes like this. Yeah, it's sold in a certain size range. Okay, so this is the available carbon steel plate. Yeah, in this range. Okay, so for us is 1.792 inch. So it's between 5/8 to 2 inches. So it will be sold in 1/8 increment. Okay, so if you look at the increment, right? So this is 2 inches. Yeah, this is 2 inches basically. So we have 1.792 inches. So it's between this and that. Yeah, it's between that two thickness. So we're going to choose the higher value. Yeah, so we're going to size the vessel, the horizontal vessel, using 1.875 inches of carbon steel plate. Okay. So once you know the shell thickness, you also know the density of your carbon steel, right? This is given. So you can calculate the mass, yeah, of your vessel. Okay, so now we know the mass is 72,500 pounds. Now we go to our cost figure. Yeah, so now let's go to the next part. So we go to this slide here. So we are here, right? 20,000, 30,000, 40,000, 50. Okay, we are here, 72,500. Okay, and we are using horizontal vessel, so we should be looking at this number. Yeah, so it's about 200,000 US dollars. Yeah, for your horizontal vessel. Okay, so for this figure, yeah, the costs that are included are the following: the cost for the nozzle, the manholes, and the supports. Yeah, the saddles. Okay, but not the internals. Yeah, also not for the platforms and for the ladders. Okay, so for the platform and ladders, you need to go to another cost figure to get the CPL. Yeah, CPL basically platform and ladders. Okay. So another thing that you have to notice here, the figure is only valid for carbon steel. So if you are using stainless steel, you need to add the material correction factor. Yeah, but for us, we are using carbon steel, so we don't have to do any correction. Okay, so the next one will be for the CPL, yeah, for the platform and ladders. So there are equation depending on the inner diameter of the vessels. Okay, so now we know the total cost of that horizontal vessels. Okay. If you don't like to look at the figures, you can also use the curve-fitted equation. Yeah, it's here. Yeah, it's the same as the one in the figure in the previous slide. Okay. Okay, so that's for horizontal vessels. So next one will be an example on vertical tower. Okay. So for this vertical tower, the DI is given 120 inches, the height is given, operating pressure, temperature also given. And now the ambient pressure is 14.5 psia, yeah, instead of 14. So we're going to do the same calculation. The only difference is with the wind load. Yeah, so I'm not going to go through the same part, right? We know how to do it. So now let's go to the wind load. Okay? So the only difference is here, yeah, starting from 0.6, yeah, between horizontal and vertical. So like I said, the outer or the external diameter is always calculated as DI plus 2.5 inches. So this is our number. And then you substitute DO to this TW equation, and you will get this number, right? So now you know your thickness for the top part of the cylinder, and thickness for the bottom part will be the thickness of the top part plus TW. So you get this number, yeah? And then you take the average of the two, and then you add the corrosion allowance, 1/8, you get this number. And then you go back to your increment, right, for the carbon steel plate. Okay, so so if you go back to the increment, right, so 1.152 inches is between these two numbers. Yeah, so you're going to choose the higher value. Okay, so that's your final thickness. You can calculate the final mass. Okay, and then the rest are the same. Okay. Okay, so this is the correlation that you can use for a tower. The one that I showed earlier is for a vessel, yeah, horizontal or vertical vessel. So the difference will be the cost of the internals for the multiple entries. Okay, and this is the correction factors for the different materials. Okay, so this is just one example. So from the plot and from the correlation, you can get the CP or the CE. So like what we learned on Tuesday, right? The cost of your equipment must include the installation and the delivery as well, so you have to multiply by the bare module factor. And then after that, you have to take into account the C index, yeah, the inflation between the costs. Okay, so this is the cost of the tower without the packing. Yeah, if you need to price your packing, you go to this our textbook, right? Section 22.5. There are cost correlation for trays, packing, and vacuum vessels. Okay, so this is something that you need to do only next semester. Okay, so I guess that's all I have. That's the end of our lecture. So I just want to let you know, right? I won't be in charge of FYDP SEM 2. Yeah? So I won't be involved much, okay? The staff in charge is my colleague, Dr. Suraj. Have you been taught by Suraj? No? Okay, he's a nice guy, so don't worry. Okay? So if you have any question about SEM 2, right, email Dr. Suraj at this email, or you can find him in the office. Yeah, basically, you need to form your groups, and you don't have to start the work until semester 2 starts. Yeah, so don't worry that you have to work during the holiday. No, it's not needed. Okay, so any question, ask Dr. Suraj. Okay, thank you again for coming.